Hi everyone. Today we're going to talk about some different measuring techniques that we use in chemistry, and we're going to start off today with precision and accuracy. Now, I think that most people have used precision and accuracy throughout their lives to describe maybe playing darts or hitting a bullseye. So I think that a lot of people sometimes though get confused between the two because they don't mean the same thing. And I think people use those terms interchangeably when they shouldn't be. So first, let's look at precision. Precision is the closeness of two or more measurements to each other. Okay, I like to say the repeatability of it. How often do you repeat the same measurement? Okay, accuracy is how close a measurement is to an actual value. Okay, and I kind of refer to this as do you hit the bullseye? Are you accurate enough to hit the bullseye? Okay, so we can kind of measure this with looking at a dartboard. Okay, if I've got my dartboard here and I'm hitting the target, all right, if I am able to hit this target right in the center, then that was an accurate shot. Okay, I was able to hit it accurately in the center. Well, what if I'm throwing my darts and I throw a whole bunch of darts over to the side there? I wasn't very accurate, was I? But what I did end up doing was throwing all of the darts in the exact same place, and I repeated it over and over again. That is precision. So maybe I might not be accurate with my throws, but I'm very precise with my throws. Okay, so our difference here is how close do you get to the bullseye and how often do you repeat that. Now, why is that important in chemistry? Well, you have to think about the equipment that we use. What if I use a scale and I have a 100-gram mass? This is a known mass. It is a counterweight and it is used for measurement. And I put it on the scale and my scale reads it to say 105 grams. Well, that scale's not very accurate. If I've got a 100-gram mass and my scale's reading 105, that's not a good thing. But if I take that mass off and weigh it again and it says 105, and I take it off and I weigh it again and it says 105, well, my scale's precise. It's getting my same values over and over again. I'm just not getting the correct value. So sometimes it's good to know if our equipment is failing us. It might be precise, and that's a good thing because we are getting repeated results. But if it's not accurate, then we also have to figure out, well, how off was it? How off was it? And that's where something called percent error comes into play. So percent error is used for determining the precision of your calculations and measurements. Okay, so sometimes we call this a measurement of uncertainty. All right, so it is a mathematical calculation of how bad was our measurement, or how bad was our equipment, or how inaccurate was our bullseye, okay? And the way we calculate this mathematically is percent error is equal to the actual value minus the measured value over the actual value. Now, sometimes your actual value can be, your measured value can be less than or more than your actual value. So you can end up with a negative number. So we're not going to worry about the negative number. So we're just going to take the absolute value of this total. Okay. Now you're going to end up with a decimal. And so what you need to do after that is multiply that value by 100 to get your percent. Okay. So let's say using buoyancy, you measure a 250 kilogram weight to be 260 kilograms. Calculate percent error. So we have a couple of numbers here. We have our measured value and we have our actual value. So our actual value is the weight, what it was made to be, which is 250 kilograms. So we're going to say 250 kilograms, our actual value, minus our measured value, 260 kilograms, over actual value, 250 kilograms. All right, so that absolute value times 100, okay? So I end up with negative 10 kilograms over 250 kilograms times 100. And then I end up with negative 0.04, my kilograms cancel out, times 100, which is just going to be 0.04 times 100, or 4%. So I had a 4% error in my measurement. So as long as you can understand what your actual value is versus your measured value, okay, or your calculated value, okay, you figure out this certain calculation. How off were you? If in chemistry, sometimes we need to know our error in an experiment. If I was supposed to get a certain value for a chemical reaction, but I didn't, then I need to know what that percent error is. Okay. The next thing I want to talk about are measurement tools. And all I really mean by this are, rulers and scales and things like that. And one of the things that we can always do, and we have always done, is we estimate. If I look here in my classroom, I can say that my classroom is such and such by a certain feet by certain feet, but it's not necessarily an accurate measurement. Okay, but I'm estimating it just by looking around and figuring out, and that's what we naturally do. So when you use an object for measuring, we always estimate one digit better than our tool. Now, if you have a digital scale, you don't want to measure. But if you're using a handheld scale or a triple beam balance, or you're using a ruler or a meter stick or a yardstick, you are going to estimate. So let me show you what I mean. Let's have a ball, just some type of a circle. And I want to measure this ball Now I want to know how big this ball is. Most people would look at this picture and say, that ball is about 1 centimeter. It's about halfway. And that's something you're allowed to do. You're allowed to estimate that halfway point. Okay? It's not in the ruler, but you are mentally looking at it and saying, it's about halfway. That's a 1 centimeter. What if I go one step better and say, I've got 0, now I have a 1, now I have a 2. Well, it's not 1 centimeter, it's more than 1 centimeter. And so most of us would say it's 1 point something. And you're allowed to say, yeah, that's 1.2 or 1.1 centimeters. You're allowed to make that estimate because you can see that it's more than what you're given in your ruler. What if you go have a ruler that's even better? What if you have .2, 0.4, 0.6, and 0.8? Well, then you could probably say, well, I think that that ball is 1.2. Is it 2 or is it more than 1.2? It might actually be more than 1.2. So you could say, I think that ball is 1.21 or 1.20. You're allowed to make that extra measurement. You're allowed to make that extra estimate. And that comes into play with our significant figures that we talked about earlier. Okay, making sure that you have significant figures matters with your measurements. If I have a really, really good ruler to measure this classroom lengthwise, but I have a really, really horrible ruler to measure widthwise, then my final answer is going to have really horrible significant digits because of how accurate one of my rulers was. Okay, so it matters what tools you're using, and it matters how much you estimate. Okay. The next thing I want to talk about is a little bit of experimental variables. And things that we've taught that you've heard before are independent and our dependent variables. Okay. And this all comes with experimentation. Our independent variable is the variable that is changed by the user, and the dependent variable is changed because of the independent variable. So if I'm controlling an experiment and I change one aspect of that experiment, like growing plants, if I change how much water the plants get, then how tall the plants get is going to be the dependent. The water is going to be the independent. So what I change is the independent. What changes in the experiment is the dependent. Okay? And as always, the control remains constant throughout. And this is something that you use to compare your results to. What should have happened had I not changed anything. Okay? With some graphing that we need to know in class here. Some types of graphs. Hopefully some of this is review that you've talked about before in other classes, in math class maybe. we talked about inverse and direct proportions in here. So our inverse proportions are when the two variables are inversely proportional to each other, which means as one increases, the other decreases. So if I am looking on a graph and I have a x and y axis here, and I am measuring how much time would it take to dig a hole with one person, with two people, with three people. As I take people away, then that time would increase and decrease, et cetera, et cetera. So on a graph, we see this relationship. We have, as one goes up, the other goes down. If I increase people, the time to build the hole goes down. If I decrease people, the time to dig the hole goes up. So that is an inverse proportion, and we can measure this on an equation with y equals k over x, where k is a constant of proportionality. Now, you can think of k as a slope or anything like that, but k remains as the constant relationship between that increase and decrease variable. Okay, so it's also important to know that you can rearrange this equation. Maybe you know the constant variable of the experiment itself, but you don't know how many men there were or how much time it took to dig a hole. So you can have x times y is equal to k, or even x is equal to k over y. You can rearrange this equation to help you solve answers. Okay. Then the last thing I want to talk about, like I said, is direct proportions. Okay. And direct proportions are the two variables increase at a constant rate. So as one increases, so does the other. Okay, as one goes up, the other goes up, and we end up with a linear relationship. Okay, and you can treat this as, a paycheck. If you make $10 an hour, you work 1 hour, you get $10. You work 2 hours, you get $20. You work 3 hours, you get $30. So that is a linear relationship. As one goes up, I work more hours, I get more money. That is a direct proportion. And this can be noted with k is equal to y over x. All right. Now, if you rearrange this equation, the k is still the constant. And like I said before, you can kind of think of k as your slope. If I rearrange this equation to be xk equals y, well, if you flip that to be y is equal to kx with a intersect point of 0, that's your slope-intercept form. So your direct proportion is a linear relationship. Okay, so again, it's important to know how you can manipulate those equations and solve for constants or solve for your x value or your y value. That is something we will be using in here in this class. So, Overall, that's about it. In the next unit, we're going to discuss the periodic table and things that we can learn from it and some of the history of it. All right. Until then, work together, help each other, and make the world a better place. See ya.